You know, when most people picture artificial intelligence, they usually imagine this like glowing, ethereal brain. Or maybe they picture a few thousand lines of pristine Python code just sitting on a server somewhere, magically thinking and learning on its own.
Oh, yeah, it's a super pervasive image. We really tend to romanticize the algorithm itself. We just
Yeah.
completely strip away the scaffolding that actually makes it functional. I usually call it the brain in a jar myth.
The brain in a jar. Okay, I love that. That is a great way to put it, actually, because you assume you just feed this jar some data and it spits out perfect predictions or,
Uh,
self-driving cars or millions of dollars.
Right, exactly. Like it's just magic.
Right. But I was looking through our sources for today's deep dive, which is this massive stack of materials designed for professionals studying for the Google Cloud Machine Learning Engineer certification. And there's this one visual that just, it completely shatters that illusion.
Ah, yes. You're
Yeah.
talking about the operational ML landscape diagram. I'd argue it's probably the most important conceptual map in the entire curriculum.
It really is. It's this diagram made up of all these boxes. And right in the middle, looking just incredibly lonely, is this tiny little red box labeled ML code.
Yeah, just one little box.
Just one. And surrounding it, literally dwarfing it from all sides, is a sprawling ecosystem of giant blue boxes representing the infrastructure. It really puts things in perspective for you, the listener. Most people think AI is all about writing that machine learning code.
But in the grand scheme of an operational system, that code is just a fraction of the work, like a tiny fraction.
Okay, so let's unpack this. What is the actual friction here? Like, why do we need so much surrounding infrastructure just to make a single model work?
Well, the friction really stems from the fact that a model trained on a laptop is fundamentally a static artifact. It represents a snapshot of the world at a very specific point in time.
Okay, so it only knows what you fed it in that moment.
Exactly. But the real world is dynamic. It's
Yeah.
messy. So those giant blue boxes represent the reality of making a model survive in that dynamic environment. You have data collection and data management because, well, without a constant, clean, validated stream of data, your model starves.
Or I guess it learns the wrong things.
Right, which is even worse. And then you have feature engineering, which is the heavy computational lift of transforming that raw data into a mathematical space the model can actually process.
Let's actually pause on feature engineering for a second because the materials emphasize this heavily. We aren't just talking about, like, turning a timestamp into a day of the week, are we?
Oh, no, not at all. We are talking about mapping massive categorical variables into high-dimensional embedding spaces, dealing with missing values in real time, and, doing it consistently across the board.
Consistently is the key word there, right?
Yeah.
Because if your training pipeline handles a missing value by, say, substituting the mean of the column, but then your live serving infrastructure handles a missing value by substituting a zero, your model is going to generate absolute garbage predictions, right?
Exactly. That is a classic case of training serving skew. The blue boxes exist to prevent exactly that scenario. And you also have model training at scale. Training a massive transformer model across hundreds of GPUs in a distributed cloud environment using architectures like ring-all-reduce. That is a completely different engineering domain than just writing a simple PyTorch script on your MacBook.
Which brings us to the real mission of our deep dive today. We are going to demystify this entire ecosystem for you. We want to shortcut your journey to understanding MLOps, which is machine learning operations.
Yeah, we're going to walk you through the entire life cycle, from building the pipelines that move the data, to orchestrating when those pipelines run, to the continuous integration and deployment that keeps the whole thing from crashing.
All the way to actually serving those predictions to the users. And to do that effectively, we kind of have to look at the intersection of disciplines required here, because MLOps isn't just one field, right?
No, it's definitely a synthesis. The source material maps MLOps at the exact dead center of a Venn diagram, combining three massive, historically siloed fields:
Which are?
data engineering, data science, and software engineering.
Okay, I was trying to wrap my head around how these three actually interact, and I kept coming back to like a race car analogy.
I like a good analogy. Lay it on me.
Okay, so if data science is the team designing a hyper-advanced, incredibly complex race car engine, so that's our tiny red box of ML code, then MLOps is building the pit crew, the telemetry systems, the fuel lines, and the track itself so that the engine doesn't explode on lap one.
The telemetry aspect is key there. I mean, the engine alone, just sitting on a workbench, it doesn't win a race. It needs constant fuel flow.
Right, which would be data engineering bringing the data pipelines.
Exactly. And it needs real-time diagnostics monitoring, tire pressure and heat. With that software engineering, bringing scalable systems, latency optimization, and CI/CD pipelines.
Yeah.
And data science obviously brings the core model prototyping, the complex math, and the metric evaluation.
But merging those three cultures has to be a total nightmare in the real world. I mean, data engineers are obsessed with throughput and data integrity. Software engineers are completely obsessed with uptime, version control, and latency.
Oh, yeah.
And data scientists, at least traditionally, they just want the highest accuracy score on their holdout dataset, regardless of how messy their Jupyter notebook gets, right?
That cultural clash is exactly why MLOps exists as a formalized discipline now. The materials summarize this perfectly. Machine learning brings the data processing and metric evaluation. Development brings the CI/CD building, the model integration, and the latency calculations.
And then operations brings the continuous monitoring, right?
Yes, continuous monitoring, user feedback loops, and model delivery. MLOps essentially forces these isolated teams to adopt a unified framework so that when a data scientist builds a great model, it can actually be delivered to a user reliably, quickly, and safely.
Without the operations team having to manually reverse engineer and rewrite the researcher's messy code?
Exactly. That used to happen all the time, and it was a disaster.
Okay, so that's the reality check for us. We know what MLOps is conceptually. It's the pit crew, the telemetry, and the track. But how do we actually construct it? Because in a real-world cloud environment, you don't just magically snap your fingers and have these three disciplines sync up perfectly.
No, you definitely don't. You build it using an automated assembly line. In this domain, we refer to this as the ML pipeline.
Right. And our sources spend a vast amount of time on pipelines. So for the listener who is architecting these systems, let's break down the mechanics. A pipeline is essentially a series of modular components chained together, right?
Yes, and it uses a domain-specific language, or DSL, to offer automation and orchestration.
Okay, so the modularity is the most critical concept here. Think of a factory floor. Raw materials, your data come in at one end. They move to station A, where they are validated.
Right, checking for errors.
Then they move automatically to station B, where features are extracted. Then to station C, where the model is trained. By containerizing and keeping these steps modular, you can update the logic in station B without having to tear down and rebuild the entire factory.
Exactly. And the specific managed tool our Google Cloud certification materials focus on for this is Vertex AI Pipelines.
Now, the sources define Vertex AI Pipelines as managed Kubeflow V2, meant to accelerate productionization. Now, I understand that Kubeflow is an open source project originally built to make deployments of machine learning workflows on Kubernetes, like simple and portable. But managing bare metal Kubernetes clusters is notoriously brutal, right?
Oh, it is incredibly demanding overhead. It requires a dedicated team just to keep it running. So when the source says Vertex AI Pipelines is managed, it means Google's control plane handles all the underlying Kubernetes infrastructure for you.
So you don't have to worry about provisioning node pools or managing pod lifecycles.
Nope. Or scaling the cluster up and down. You just write your pipeline code using the SDK, hand it to Vertex AI, and it handles all the heavy lifting of container execution and data passing between the steps.
But there's a significant architectural debate in the materials about which toolkit or SDK you should actually use to write that pipeline code, because Google supports a couple of different paths here.
This is a foundational decision point for any ML engineer. The great SDK debate basically splits between TFX, which stands for TensorFlow Extended, and the Kubeflow Pipelines SDK.
And the rule of thumb provided is pretty stark. It suggests that if you are using TensorFlow to process terabytes or even petabytes of structured data or text, you should default to TFX. Why is that? What makes TFX capable of handling that kind of sheer volume?
Well, TFX is designed from the ground up for massive Google-scale data processing because it is deeply integrated with Apache Beam under the hood.
Wait, Apache Beam, isn't that a big data thing?
Yeah, it's a unified programming model for both batch and streaming data processing. When you write a TFX pipeline, the data validation and transformation steps aren't just running in a single Python container on one machine.
Oh, they aren't.
No, they're compiled into distributed processing jobs. So if you are chewing through petabytes of log data to train a massive deep learning model, TFX leverages the distributed execution graph to process the data in parallel across hundreds of workers simultaneously.
Wow. So it's essentially bringing heavy-duty big data engineering tools directly into the ML pipeline?
Exactly.
But the materials are clear that for almost all other use cases, you should go a completely different route.
Yes. For almost everything else, the recommendation is to build using the Kubeflow Pipelines SDK and specifically leverage Google Cloud Pipeline components.
But why the pivot? If TFX is so powerful and scalable, why not just use it for everything?
It comes down to flexibility and adoption overhead. TFX is heavily opinionated, and it's tightly coupled to the TensorFlow ecosystem.
Ah, I see.
So if your data science team is writing models in PyTorch or XGBoost or scikit-learn, forcing them into TFX is like trying to fit a square peg into a round hole. It's frustrating. The Kubeflow Pipelines SDK, on the other hand, is completely framework agnostic.
Meaning it doesn't care what math libraries you use.
Right. It's also generally much easier for teams to adopt because you can wrap almost any standard Python code into a Kubeflow component without having to learn all the complex Apache Beam semantics.
Okay, let's make this tangible for the listener. Let's say we've chosen Kubeflow, and we want to build a pipeline on Vertex AI. The materials walk through the logic of chaining components. Let's explore the mechanics of how these steps actually interact rather than just reading the code syntax.
Sure. So the process starts by defining the raw material. You might have a step that reaches out to a cloud storage bucket to create a managed dataset object.
Now, this isn't just downloading a CSV, right?
No, not at all. It's registering a metadata object within Vertex AI that says, hey, here is the exact state and location of the data we are going to use for this specific run.
Okay, so we have the data registered. But the next step is where I find the mechanics really fascinating. If we pass that dataset object into a training component, say, like an AutoML image training job, how does the pipeline physically pass the data from step 1 to step 2? Because they are running in completely isolated containers, right?
That is a fantastic architectural question.
Yeah.
You're right, they are isolated, and they definitely don't pass the heavy data directly to each other over a network request.
Yeah, that would crash the system if you're moving terabytes of images.
It would be a disaster. Instead, they use a system of references managed by the Vertex ML metadata store. Step 1 processes the data, writes the output to a specific unique path in cloud storage, and then passes the URI pointer of that storage location to the metadata store.
Oh, I get it. Just the address.
Exactly. Then step 2 spins up, reads the metadata store, gets the URI, and pulls the data directly from storage. It's a highly decoupled, stateful way of managing data flow without overwhelming the network.
That makes perfect sense. And regarding that training step, if we are using an AutoML component, we aren't writing custom neural network layers manually. The component is handling the architecture search for us.
Right. Under the hood, AutoML is performing a neural architecture search. It's essentially using machine learning to design the machine learning model.
Which always sounds a little bit like sci-fi to me.
It kind of is. It allocates compute, tries different architectures,
Right.
maybe a ResNet variant, maybe an efficient net variant, evaluates their performance against your validation data, and then outputs the optimal trained model artifact.
Okay, so once that optimal model artifact is produced, it needs a place to live where outside applications can actually reach it. And this requires provisioning an endpoint.
Yes. Before a model can serve predictions to users in real time, it needs dedicated serving infrastructure and a secure address. An endpoint component provisions that underlying hardware, the VMs, the load balancers, the accelerators, and it provides a URL where your application can send JSON payloads and receive predictions back.
And then the final piece of this chain is the actual deployment component, which takes a model artifact from the training step and loads it onto the endpoint we just provisioned. I noticed in the architectural specs, this step allows you to configure minimum and maximum replica counts.
Those replica counts are vital for operational stability and, honestly, for cost control. A replica is basically a copy of your model running on a node within that endpoint cluster.
So by setting a minimum of, say, 2 and a maximum of 10, you are configuring horizontal pod autoscaling.
Precisely. As incoming API traffic spikes, the load balancer detects the increased CPU or GPU utilization and automatically spins up more replicas to handle the load, up to your maximum of 10.
And then when traffic drops at night and nobody is using the app,
It scales back down to 2, saving you a ton of money.
it's incredible how much infrastructure orchestration is just abstracted away behind a few component calls. The materials actually test this knowledge with a scenario. Imagine you have a pre-trained XGBoost model sitting on your local machine, and you want to upload it to the Vertex AI model registry and deploy it for online inference using the absolute simplest approach possible, like no custom serving containers, no complex pipelines, just get it online.
The trap here is over-engineering. Engineers love to write custom REST APIs or complex Docker files. But the Google Cloud ecosystem provides pre-built components for exactly this use case.
So what's the answer?
You just chain a model upload component and a model deploy component. You point the upload component to your XGBoost model file, it registers it, and instantly passes the registered model reference to the deploy component, which handles all the serving infrastructure. It's a test of knowing when to leverage managed services rather than building from scratch.
But bridging those managed services introduces massive complications when teams don't share the same tech stack. Let's push this logic a bit further. You're at an enterprise where the data engineering team has spent 2 years building an incredibly robust, complex feature engineering pipeline using PySpark, and they run it on Dataproc serverless.
Okay, a very common scenario.
Right. But the data science team, naturally, built the model training architecture as a Vertex AI custom job using TensorFlow. Currently, these are completely disjointed systems. How do you orchestrate a single pipeline that seamlessly spans Dataproc and Vertex AI without forcing one team to rewrite all their code?
This is the reality of modern enterprise architecture. You absolutely do not rewrite the code. That would take months. You use the Kubeflow Pipelines SDK to wrap the existing workflows. Kubeflow basically acts as an overarching control plane here.
So you aren't moving the code, you're just pointing at it.
Exactly. You define one component that executes the Dataproc serverless batch job. You define a second component that launches the Vertex AI custom training job.
But how does Kubeflow know to wait for the Spark job to finish before launching the TensorFlow job? Because if the data isn't ready, the model training fails.
Through explicit dependency mapping. When you build the pipeline graph in Python, you simply declare that the output of the Dataproc component is an input to the Vertex component. The Kubeflow orchestration engine interprets that graph.
Oh, so it just reads the relationships.
Right. It fires off the Dataproc job, monitors its state via the API, and puts the Vertex job in a pending state. Only when Dataproc returns a success signal and registers the output data location does Kubeflow spin up the compute for the TensorFlow job. You've created a single trackable execution graph over 2 entirely different distributed computing environments.
That is a powerful level of abstraction. But what if a data science team isn't using a managed framework at all? What if they have highly bespoke Python code, relying on obscure, specific versions of scientific libraries, and they need to integrate this custom logic into a Kubeflow step?
This is where we have to discuss the mechanics of containerization. The solution here is to package that bespoke Python code into a Docker image.
Why is Docker the silver bullet here? Like, why can't Kubeflow just execute the Python script directly?
Because of the environment dependency nightmare? If your script relies on a specific version of Pandas, a specific CUDA driver for GPU acceleration, and maybe a custom C++ compilation maker.
Yeah, that sounds like a headache.
It is. Trying to install all of that on a generic Cloud Worker node every time the pipeline runs is incredibly fragile. It will inevitably break. A Docker container packages the operating system, the exact library versions, the environment variables, and the code into one immutable image.
So Kubeflow doesn't need to understand anything about the complex math or the obscure libraries inside your code. It just pulls the Docker image from a registry, mounts the inputs, and executes the entry point.
Precisely. Once your code is containerized, you use a Kubeflow SDK function to load the component directly from the container specifications. It guarantees that the code will execute identically on a massive cloud cluster as it did on the developer's laptop.
Okay, so we've bridged the framework gaps using components and containers. But this introduces a massive financial problem that I think we need to address. Let's say you have a pipeline that preprocesses 10 terabytes of data, and it takes a full hour of heavy, expensive compute time across a cluster of machines just to crunch that data.
That's a hefty processing bill.
Exactly. After that hour, step 2 runs, which is training the actual model. But during the experimentation phase, the data scientists are just tweaking the model parameters. They change the learning rate, adjust a few hyperparameters, and rerun the entire pipeline to see what happens.
I see where this is going. If they run it 20 times, they are paying for 20 hours of processing those same 10 terabytes of data, even though the raw data and the preprocessing logic haven't changed a single byte.
Exactly. It's a fast track to bankrupting a startup. How does the architecture prevent this redundant, wildly expensive compute?
The mechanism that solves this is execution caching. backed by the Vertex ML metadata store. In Kubeflow, you can enable caching at the pipeline level. When caching is enabled, the orchestration engine performs a very specific check before it spins up the compute for any component.
What exactly is it checking? How does it know if the data is identical? I mean, it can't possibly scan 10 terabytes of data in a few seconds to check for changes.
No, it doesn't scan the data. It uses cryptographic hashing. When a component runs for the first time, the system hashes the component's underlying code, the exact container image signature, and the metadata signatures of all the input.
Okay, a hash is like a unique digital fingerprint.
Yes, it stores this combined hash in the metadata store alongside the location of the final output. The next time the pipeline runs, it recalculates that hash based on the current inputs and code.
Ah, and it queries the metadata store. If that exact hash exists, it knows with absolute mathematical certainty that this exact operation has been performed before.
Exactly. And if it finds a match, it intercepts the execution. It completely skips provisioning the compute nodes for that 1-hour pre-processing step. Instead, it just retrieves the URI of the previously generated output from the metadata store and immediately hands it to the next step.
Wow. So the developer can enable caching for the heavy data processing steps, but disable it for the model training step where they are actively changing the code. They get a lightning-fast save point in a massive industrial process, saving massive amounts of time and compute costs.
It fundamentally changes the iteration speed of a data science team. It's a game changer.
All right, so we have a pipeline that is modular, it bridges frameworks via containerization, and it's highly optimized for cost using metadata caching. We are in great shape, but we are still manually triggering these runs.
Right. Someone is still pushing a button.
Exactly. To reach true MLOps maturity, the system has to react to the world automatically. We have to move from building pipelines to orchestrating their lifecycle.
This transition is where we move into advanced CI/CD, continuous integration, and continuous delivery. The materials outline the ML development lifecycle in 3 distinct phases: experimentation, training formalization, and training operationalization.
Let's bypass the experimentation phase, since we all know what a data scientist hacking away in a Jupyter notebook looks like. Training formalization is what we just discussed, turning that notebook code into reproducible Kubeflow components. But the final boss is training operationalization. This is where CI/CD comes in. But CI/CD in the machine learning world is vastly more complex than in traditional web development, isn't it?
Oh, it is significantly more complex because you aren't just testing code. You are testing data expectations and mathematical convergence. In traditional software, continuous integration runs unit tests to ensure a new function doesn't crash.
Just checking if the code compiles, basically.
Right. But in MLOps, CI means unit testing your feature engineering logic. It means testing the pipeline construction code itself to ensure the graph compiles. But most importantly, it means validating the model interface.
Wait, what do you mean by the model interface?
Well, if your new model architecture expects a tensor shape of 256 by 256 pixels, but the downstream serving application is still sending 128 by 128 images, the system will crash in production. The CI pipeline must automatically build the Docker containers, run a dummy data set through the pipeline, and verify that the input and output schemas perfectly match what the production environment expects.
Okay, so CI proves the code and the schemas are valid. Then we move to continuous delivery, or CD, the deployment of the artifacts, and the source details a progressive delivery workflow. Because you don't just push a newly trained model to production and hope for the best, right?
Never. The risk is way too high. A model might pass all CI checks, compile perfectly, and still be fundamentally broken in a live environment. Progressive delivery means automating a staged rollout. You deploy the model to a staging environment first. You run automated acceptance testing, and crucially, you run smoke tests.
Let's dig into smoke testing, because it's a term borrowed from hardware engineering, but it has a very specific application in ML serving. We aren't testing for accuracy here, right?
Correct. We already validated the model's accuracy metrics during the training pipeline evaluation step. Smoke testing in the CD pipeline is heavily focused on model service efficiency. We are testing the physical limits of the serving infrastructure.
How do you do that?
We inject a massive simulated payload of requests to measure the P99 latency.
P99 latency, so that's the time it takes for the slowest 1% of requests to complete.
Yes. If the model is highly accurate, but the P99 latency jumps to 5 seconds per request, it will break the upstream application. Users won't wait 5 seconds. We also test throughput saturation. How many requests per second can the endpoint handle before it starts dropping connections or throwing 500 errors?
And what happens if the newly deployed pipeline fails those smoke tests? The CD pipeline is automated, so how does it handle a failure without bringing down the live application?
The CD orchestration layer must have an automated rollback mechanism configured. If the latency thresholds are breached during smoke testing, the CD pipeline instantly aborts the rollout, flags the deployment as failed, and ensures the production load balancer continues routing 100% of traffic to the model produced by the previous successful training run.
It's a comprehensive safety net, so we have CI and CD, but MLOps has a third C that is unique to this field: continuous training.
Yes. Continuous training is the defining characteristic of a mature MLOps system. It means triggering the entire pipeline, not just when a developer pushes new code, but automatically in response to changes in the real world.
Let's look at the mechanics of how we actually wire these triggers up. The materials present a scenario where a team is collaborating on GitHub. They push a new commit containing updated feature engineering logic. How do you architect a system that links a Git push to a massive Vertex AI training pipeline?
This requires a dedicated orchestration service. In Google Cloud, the backbone for this is Cloud Build. You configure a Cloud Build trigger to listen for specific webhooks from GitHub, for example, a push to the main branch.
So Cloud Build acts as the listener. When the developer pushes the code, GitHub sends the webhook and Cloud Build catches it. What happens next?
Cloud Build spins up a secure execution environment and begins stepping through a defined YAML configuration file. First, it might execute standard unit tests. If those pass, it moves to the heavy lifting. It uses Docker to build the new container images for your Kubeflow components, injecting the new code from GitHub.
And it needs a place to store those newly built containers.
Yes. Cloud Build pushes those containers to Artifact Registry, which is a secure, centralized repository for managing container images. Finally, the last step in the Cloud Build YAML uses the Google Cloud SDK to submit a new pipeline job to Vertex AI, explicitly pointing it to the fresh containers it just stored in Artifact Registry.
So the entire process from Git push to a distributed training job running in the cloud is entirely hands-off.
Completely hands-off.
That handles code changes perfectly. But what if the trigger isn't a code change? The materials present another common architecture problem. You have a pipeline that should only run when a batch of new data files arrives from a third-party vendor into your cloud storage bucket. You can't schedule it for Sunday night because the vendor is unreliable. Sometimes the data arrives Monday morning. How do you trigger the pipeline based purely on the arrival of data?
This is an event-driven data pipeline problem. You wouldn't use Cloud Build for this because there is no code change. The optimal architectural choice here is to deploy a directed acyclic graph, or DEAR, using Cloud Composer.
Let's break down Cloud Composer because it's a massive tool in the data engineering space. It's essentially Google's managed version of Apache Airflow, right?
Yes, Airflow allows you to build complex flowcharts, those DAGs, where you define tasks and their dependencies in Python. The scheduler orchestrates when these tasks run across a pool of worker nodes.
And how does Airflow detect the file arrival?
Airflow provides a vast library of operators and sensors. To solve this specific problem, you would implement a GCS object update sensor within your DAG. This sensor task essentially polls the specified cloud storage bucket at regular intervals.
But doesn't constant polling run up compute costs? I mean, just having a machine constantly checking an empty bucket.
It can, which is why you have to configure the sensor's pooling interval intelligently and often use a feature called reschedule mode, where the sensor releases its worker slot between polls, so you aren't paying for an idle compute node just waiting for a file.
Oh, clever.
Yeah. The moment the sensor detects the new object metadata in the bucket, it marks its task as successful. The Airflow scheduler sees that success, moves to the next node in the DAG, and executes an operator that triggers the Vertex AI pipeline.
It's an elegant way to ensure you only pay for the heavy pipeline compute when the raw materials are actually present.
Exactly.
All right, so let's take a breath. Our model is trained, it's been rigorously tested through CI/CD, the data flow is automated, and the model is deployed to an endpoint. The engineering work is done.
The infrastructure work might be stable, but the core objective hasn't been met yet. A model sitting on an endpoint doesn't generate business value.
Good point.
It has to actually serve predictions to applications and handle real user traffic. This brings us to the final and arguably most critical phase of the deep dive: prediction serving and online experimentation.
This is where the model finally hits the real world. And the materials outline 4 entirely different architectural patterns for serving predictions, depending on the latency and throughput requirements of the business application. We need to explore the mechanics of each.
The first and most common pattern is online inference. This is designed for real-time, high-frequency singleton requests.
Give me an example of the architecture here.
Imagine a translation app on your phone. You speak a sentence, the app sends that single audio payload to an API, the model processes it, and sends the translated text back instantly. The architectural priority here is minimizing latency. Every millisecond counts.
And to minimize that latency, I noticed the materials emphasize choosing the right communication protocol. You don't just default to standard REST APIs for high-performance online inference. You use gRPC. Why is gRPC faster?
It comes down to serialization. REST APIs typically send data formatted as JSON, which is plain text. JSON is easy for humans to read, but it is incredibly bulky, and parsing text is computationally expensive for the server.
It takes time to read the words.
Right. gRPC, on the other hand, uses protocol buffers. It serializes the payload into a highly compressed binary format before it leaves the client. It strips away all the bulky text formatting. When the binary payload hits the Vertex AI endpoint, it can be deserialized and processed by the model in a fraction of the time, resulting in sub-millisecond network transit overhead.
That makes total sense. Text is heavy, binary is light. So that's online inference. The second pattern is streaming inference. How does this differ architecturally?
Streaming is for near real-time event processing, usually involving a continuous flow of data rather than isolated requests. Imagine a credit card fraud detection system. It isn't just looking at a single transaction in isolation, it's constantly analyzing a stream of transactions happening globally, looking for anomalies within a specific time window.
And the architecture for that relies heavily on message queues, right? The classic pub-sub model.
Exactly. You use Google Cloud PubSub. Think of PubSub as a massive, high-speed restaurant kitchen ticket wheel. Transactions are constantly being slapped onto the wheel. You then have a stream processing engine like a cloud function or a Dataflow streaming job acting as the line cook.
I love that analogy.
It pulls a batch of tickets off the wheel, processes them through the model, and outputs the fraud probability. This architecture decouples the ingestion of the events from the processing, allowing the system to absorb massive spikes in traffic without overwhelming the model endpoint.
That's a great visualization. The third pattern is offline batch inference. This is where we throw latency requirements out the window and focus entirely on throughput.
Yes, this is bulk data scoring. You don't need the answer instantly. Maybe you are a massive streaming service, and every night at 2 a.m., you need to run your recommendation model over your entire database of 50 million users to calculate what movies to display on their homepage the next morning.
And how do we architect that? We wouldn't send 50 million individual gRPC requests to an endpoint, would we?
Absolutely not. That would be incredibly inefficient and expensive. For massive batch scoring, you rely on distributed processing architectures like Dataflow or BigQuery ML.
Okay, how does that work physically?
If your data is stored in massive T-record files in cloud storage, you use Dataflow. Dataflow provisions a massive pool of worker nodes. It partitions the T-records, distributes the chunks to the workers, and each worker runs the model locally against its chunk of data in parallel. It then aggregates the results and writes them efficiently into a data warehouse like BigQuery. You maximize raw throughput and shut the cluster down when the job is done.
And the final pattern is embedded inference.
This is pushing the model all the way to the edge. The model isn't running in a cloud container at all. It's running directly on the silicon of a user's mobile phone or inside a low-power IoT device in a remote factory.
This requires entirely different model optimization, right? You can't run a 10 gigabyte neural network on a thermostat.
Exactly. This is where you use frameworks like TensorFlow Lite. You perform quantization, which reduces the precision of the model's weights from 32-bit floats to 8-bit integers,
Which means it takes up way less space.
drastically shrinking the model's size and memory footprint so it can run on edge hardware. It's critical for situations where you need zero network latency, or you don't have a reliable internet connection, or for strict privacy requirements where user data cannot leave the device.
Okay, so those are the 4 serving patterns. But the serving infrastructure isn't just the model and the compute. The materials heavily emphasized surrounding architectural components. The most prominent one is the feature store. Why is a feature store absolutely critical for online inference?
It solves a massive latency bottleneck. Imagine your fraud detection model needs to know a user's average spend over the last 30 days to make a prediction. When a transaction request comes in, you don't have the 5 seconds it would take to query a massive relational database, run a SQL aggregation across millions of rows, and calculate that average. You need the answer in milliseconds.
So how does the feature store solve that?
A feature store is essentially a high-speed, dual database system. It has an offline layer for training, but more importantly, it has an online serving layer. usually backed by a low-latency key-value store like Redis. Data pipelines constantly pre-calculate that 30-day average in the background and push the updated value into the online feature store.
Ah, so it's ready and waiting.
When the prediction request hits the model simply makes a microsecond key-value lookup to the feature store to retrieve the pre-calculated feature. It guarantees low-latency serving while ensuring the features used for serving perfectly match the logic used during training.
That is brilliant. It completely decouples the heavy analytical processing from the real-time serving path. Another surrounding component mentioned is explainability. In many industries, it's not enough for the model to just output a probability score. It has to provide the mathematical rationale for the prediction.
Explainability is non-negotiable in regulated industries like finance or healthcare. Why was this loan denied? Why is this transaction flagged?
So how do you do that technically?
Vertex Explainable AI uses techniques like Shapley values or integrated gradients to calculate the feature attribution. It essentially reverse engineers the prediction and tells the application, hey, the model denied this loan primarily because the debt-to-income ratio feature contributed 45% to the final decision.
Okay, so we have the serving architecture, the feature store for low latency, and explainability for compliance. But even with all of that perfectly engineered, you still don't just route 100% of your live user traffic to a brand new model. The materials cover several online experimentation strategies to safely test a model in the wild.
This is where we move from infrastructure risk to business risk. A model might be fast and stable, but if it recommends the wrong products, revenue drops. The safest way to test this is a shadow deployment.
I love the mechanics of shadow deployments. Explain how the traffic routing works here.
In a shadow deployment, the load balancer is configured to mirror the incoming user requests. The request goes to the existing trusted production model, and the response is sent back to the user. But a copy of that exact same request is simultaneously routed to the new experimental model.
But the user never sees it.
Right. The new model processes the data and generates a prediction, but that prediction is never shown to the user. It is simply logged in a database.
So it completely eliminates any risk to the user experience. You let it run for a week, and then data scientists can query the logs to compare how the new model would have performed against the old model on identical real-world traffic.
Exactly. It's the ultimate zero-risk testing environment. Once you're confident in the shadow performance, you might move to a canary deployment.
Like a canary in coal mine.
Precisely. You configure the traffic splitting at the endpoint to route, say, 5% of your live user traffic to the new model and 95% to the old model. You monitor the business metrics and error rates closely. If the canary crashes or conversion rates plummet, only 5% of users were affected, and you can instantly roll back.
And if it works?
If it performs well, you gradually scale the traffic split 10%, 25%, 50%, until the new model handles everything.
Then you have classic A/B testing, which is similar, but usually involves a fixed 50-50 split to statistically measure which model drives more revenue over a set period of time. But the most mathematically complex experimentation strategy mentioned is MAB, or multi-armed bandit testing. This isn't just simple traffic routing.
No, multi-armed bandit is a fascinating application of reinforcement learning applied to the deployment process itself. It solves a major flaw in traditional A/B testing.
Which is what? The opportunity cost.
Exactly. In a traditional A/B test, if Model A is significantly worse than Model B, you are still forcing 50% of your users to experience the inferior Model A for the entire duration of the 2-week test. You are actively losing revenue to achieve statistical significance.
So how does a multi-armed bandit architecture fix that? Let's get into the mechanics of the algorithm.
A MAB system dynamically adjusts the traffic split in real time based on the ongoing performance of the models. It balances two competing mathematical concepts, exploration and exploitation. It uses algorithms like epsilon greedy or Thompson sampling.
Let's break down Thompson sampling because it perfectly illustrates the concept of Bayesian updating.
In Thompson sampling, the system maintains a probability distribution for the expected success rate, say, the click-through rate of each model. When the test starts, it doesn't know which model is better, so the distributions are broad, and it splits traffic evenly. This is the exploration phase.
But then it starts learning.
Right. As users interact, the system updates its beliefs. If Model B starts getting more clicks, the probability distribution for Model B shifts higher and becomes narrower, meaning the system is more confident it's the better model.
And as it becomes more confident, it shifts to the exploitation phase.
Right. The routing engine mathematically recalculates the odds and automatically starts sending 60%, then 70%, then 90% of the traffic to Model B to maximize immediate revenue. But it never fully abandons Model A. It still occasionally sends a fraction of traffic to Model A just in case the underlying user behavior changes and Model A suddenly becomes better. It continuously learns and optimizes the routing without human intervention.
It's an incredibly elegant mathematical solution to a massive business problem. And it brings us full circle. We have covered an immense amount of architectural ground today.
We really have.
Let's synthesize this journey for the listener. What this entire certification prep material is trying to hammer home is that MLOps is not about the tiny red box of ML code. It is a massive, interconnected, highly orchestrated ecosystem. It is the engineering rigor required to build robust CI/CD pipelines that validate not just code, but data schemas.
And it's understanding the deep mechanics of execution caching in the Vertex ML metadata store to save thousands of dollars in compute.
It's knowing when to use the distributed power of TFX and Dataflow versus the flexibility of Kubeflow. And finally, it's architecting serving layers using gRPC, feature stores, and multi-armed bandit testing to deliver predictions safely and efficiently to the real world.
It is a marvel of modern engineering when all these systems synchronize. And I want to echo the advice from the final slide of the curriculum we reviewed. It simply says, enjoy the journey as much as the destination. Mastering MLOps, understanding how containerization, orchestration, and machine learning all breathe together is a marathon. It requires a fundamental shift in how you view software architecture.
It's definitely not something you master over a weekend by watching a few tutorials. It takes deep, foundational engineering knowledge. Well, to close this out, we've talked a lot about automation today. Systems that automatically trigger distributed training pipelines. Systems that automatically deploy via reinforcement learning. Systems that automatically fall back if latency spikes. Given all of that, I want to hand it over to you for one final thought for our listeners to ponder. Where is all this automation leading us?
It's the inevitable next question, isn't it? If we are building orchestration layers that are this mathematically sophisticated layers that can monitor data drift, evaluate model performance, and dynamically adjust serving traffic using algorithms like Thompson sampling, at what point does the MLOps pipeline start acting as its own machine learning engineer?
Oh, wow.
We are rapidly approaching a horizon where the orchestration layer itself will use deep learning to optimize the very CI/CD processes, hardware provisioning, and architecture searches we just spent the last hour discussing. It's an Inception-like concept, but it is the definitive future of the field. Something to seriously mull over as you build your next pipeline.
A fascinating place to leave it. Thank you for joining us for this deep dive into MLOps. Until next time.